Okay, so welcome to Math 317. This is Operations Research, Lecture 29. So what we're going to do today is we're going to go through carefully and talk about the runtime of the Gale-Shapley algorithm. And what I want to do is not just go through the math, but just try to drive home just how phenomenal this result is. And so one of the things it says is eventually in the most n squared minus 2n plus 2 steps. Okay, well, I'm actually not able to quickly see why it is equal to that. I can see why it's, I think, n squared minus n plus 1, something like that. I can see something close to that. But when you see something like n squared minus 2n plus 2, what really matters? The n squared. The minus 2n plus 2 doesn't really matter too much. Now, again, you should always check special cases. What's a really simple case of n that you should be able to check by hand? 1. So if there's one man and one woman and you need to match, how many steps should it take? It should take just 1 step. Good, the formula at least works in that case. And so what I did here is I plotted n. And then over here, I plotted n squared minus 2n plus 2 over n. And so you can see very quickly the ratio of n squared minus 2n plus 2 over n gets very close to 1. So you're already, by the time n is around 40 or 50, we're really not seeing much of a difference. Okay, for small n, sure, but for reasonable n, it's not so bad. How many ways could you assign or match n men with n women? Well, n choose n is 1, so that's saying there's only one way we can do it. So n choose 2 would be, you take n objects and you choose 2 of them. So I have n men in one group, I have n women in another group, and I want to assign it so every man is matched with one woman, every woman is matched with one man. So 2n choose n would mean I have 2n people total, and I'm choosing a subset of n from them.
We have n women and n men.
Right, so 2n choose n would just be put everybody together and you're just choosing a set of n people. We have n men and n women. How many ways can you match n men with n women so that every man is matched with one woman, every woman is matched with one man? You're going to kick yourself. You're making it too hard. Go person by person. How many choices are there for the first man? And well, okay, well, okay. So how many choices are there for the first person? N, right? The first guy can be matched with n women. Once he's matched, you now move to the second guy. How many women are left? N minus 1. And you keep going and you keep going and you keep going. So the number of ways to match n people with another set of n people is just n factorial. If you want to think of it as for one of the groups, you can just have them numbered 1 through n. And for the other group, you just randomly permute the numbers 1 through n, and every permutation is going to be a legitimate matching. So over here, what I've done is I've plotted as a function of n squared over n factorial. So, it takes, n squared, steps at most. There's n factorial possible. So just get a little bit of a sense, if I wanted to look at all n factorial possibilities, that would take a long time once n is even modestly large, like 10. Once it gets up to 20 or 30, forget about it. And so I wanted to try to plot n squared divided by n factorial to just give you a sense of how much faster n factorial is growing than n squared. Does this plot really give you much information? No, why not? So what's the danger of looking at this? Why is this not so useful? So you're looking at it, so something must be causing you trouble. Why can't you use this to really discern what's going on?
N squared over n factorial. If there's 2 separate graphs, one for n squared versus n, and one for n factorial versus n. Pretty easily discern how much faster n factorial is.
Okay, but why? What's the difficulty? What's the problem when we're looking at this? So you always want to be able to look at an image. What does this tell you about the growth rates of n squared and n factorial? Grows a lot faster. Can you tell how much faster by looking at this? Why not? Yeah, I mean, it's so close to 0. I can't tell. Is it 1/10, 1,000th, 1/billionth, 1/trillionth, 1/10⁻²? Because n factorial is growing so much faster, when I look at this, it's indistinguishable from 0. When I try to view this, I just can't really see anything. What could I do to this graph so that I could really understand it? What could we do to this graph so that it would become more understandable? But I would still have this trouble with scale. It's decaying so rapidly here that if I try to plot n squared divided by n factorial versus n, it's going to be hard to see anything. What can I do to transform the data so that I can read this? Do a log transform. Plot the log of n squared over n factorial, either against the log of n or against n. Right? When you have something going across so many orders of magnitude, if you do a logarithm, it's going to be much easier to see what's happening. So on the next slide, I tried to put in a little bit of numbers. So I did a little bit of searching. It said there's about 10 to the 80 particles in the observable universe. If you go up to including photons and whatnot, maybe around 10 to the 89, there's about 10 to the 50, I think, atoms in the Earth, just to give you a sense of numbers. Okay, 10 to the 50, it's about how many atoms we have on the Earth. 10 to the 89, maybe number of doohickeys in the universe. Okay. Doohickey is a thingamabobmagic. It's just anything. Just count all the objects in the universe, anything. Quarks, electrons, photons, how many objects are there in the universe? So here's a plot of the log of n squared over n factorial base 10, and here's n. And so, the first line, let's call it gold, that's at around -50. That's about the number of atoms on the Earth. So when you're looking at the ratio of n squared over n factorial, when n is around maybe 44, give or take, the ratio is about 10 to the -50. So to put that in perspective, I'm sorry? That's basically saying I'm thinking of a specific atom on the Earth. Just to give you a sense of the scale of this, you've got to identify the atom I'm thinking of. When you hit, you're not even at 70, you're already thinking of now a specific doohickey in the observable universe. That should give you some sense of just how much faster n factorial is growing than n squared. If we brute force all the possibilities and look at all n factorial matchings, and we compare that to just using the Gale-Shapley algorithm, which takes n squared steps, and look at a ratio of what this is. You're talking about choosing a specific atom on Earth or a specific object in the universe. So I really hope this drives home just how efficient something like this is. You do not want to try to figure out which atom I was thinking of. I'll make it easy for you. It's in my visual site. Still not going to be even remotely doable. All right. So do you want to do a specific example where we go through a matching? Okay. So here, hopefully it's visible. We have Elizabeth, Jane, Lydia, Charlotte. We have Bingley, Darcy, Collins, and Wickham. And so the way it works is the men propose to the women, and the women do not accept a proposal. What they'll do is they'll put someone and say, okay, of all the people who've proposed to me in this round, you are the best to date. You can take that sentence two different ways. And I will keep you on string for now. I'm not going to reject you, but I'm not going to accept you. So we have Elizabeth, Jane, Lydia, and Charlotte. And now the men propose. So who does Bingley propose to? Bingley proposes to Jane. They all have different first names. So Bingley proposes to Jane. Darcy proposes to Elizabeth. Collins proposes to Jane. And Wickham proposes to Lydia. So what happens? So what happens in stage one? Jane has to choose. So who's Jane going to choose? Bingham or Collins? Bingham. I just see Collins is listed last for Jane. So I know Jane is going to choose Collins. So now Collins has to propose. So who should Collins propose to in round two? Collins can't propose to Jane, so who does Collins propose to?
Elizabeth.
Proposes to Elizabeth. So now we have Darcy and Collins, and nobody else was proposing.
So each girl only, like,
You-
only one baby per round.
Only one maybe per round, right? Each woman is going to take the highest available suitor. And so now,
You have to have more than one offer to make it maybe, or could hypothetically Elizabeth make a baby for?
so if Elizabeth has offers, she's going to reject all but one offer, and then that offer she's just going to keep on a string. Now, some people may not have any offers. I don't know what's wrong with Charlotte. It's been far too long since I've read Pride and Prejudice. What is Elizabeth going to do now that she has offers from both Darcy and Collins? She's going to say maybe to Darcy because she rates, I really should reread, no, I shouldn't, but Collins seems to be very poorly rated by everybody, fourth place, fourth place, fourth place, third place. All right, so Elizabeth is going to keep Darcy as a maybe, and Collins is going to be rejected again. What is Collins going to do now? Lydia. So now it's going to be Darcy, Bingley, and then Lydia is going to have Wickham and Collins. Are things going any better for Collins? No, Lydia looks at it and goes, oh, Collins, no, thank you. I will go with Wickham. And so now we're on the fourth stage. And so Darcy, Bingley, Wickham, and Collins has no choice, proposes to Charlotte. And at this point, everyone now has a proposal. And now that everyone has a proposal, now we lock in. And we now have our assignment. So Elizabeth gets Darcy, which I do remember worked out. And then Jane has Bingley, Lydia has Wickham, Charlotte has Collins. And then you can check and see, is this stable? Is there a chance that Charlotte and Collins could mutually switch with anyone? This is going to be very easy to see that the answer for that one is no, because I think I can say this: Collins is a loser. Nobody really wants Collins. The only person who didn't put Collins dead last was Charlotte, who Collins is now associated with. So there's no danger that anyone is going to want to switch with the Charlotte Collins pair. Is it possible that Charlotte would rather have someone else? Yes, Charlotte would much rather have either Bingley or Darcy. But that would mean either Bingley or Darcy would have to dump who they have and take her, which they're fine with. They might be willing to do that. But at the same time, in order to do the switch, someone would have to take Collins. So she would need either Elizabeth, Jane, or Lydia to want to take Collins. And since they all rank Collins as last, there's no chance of that happening. To show that it's stable, how many different pairs do we have to look at? Why 3? Well, we have to be unstable. There have to be two pairs where both are willing to switch. So how many ways can I choose two pairs from the four pairs? 6. There's 4 choose two pairs. So we just check all 4 choose two pairs. The columns are easy.
Just like the quick mental math for the 4 choose 2.
So I have 4 pairs. I have Elizabeth and Darcy.
No, I mean like calculation with 6.
Right, that's what I'm saying, is I have 4 pairs, Elizabeth, Darcy, Jane, Bingham, so there's 4 pairs. How many ways can I choose 2 objects from 4? That's just 4 choose 2. Right, I have 4 objects, 4 pairs. I need to choose 2 of the 4 pairs. And so what's 4 choose 2? It's 4 factorial over 2 factorial, 2 factorial.
Yeah, that's
Right.
That's fine.
Yep. It's 4 factorial over 2 factorial, 2 factorial. And so that just becomes 6. So there's 6 pairs to check. 3 of them we've already checked. We quickly checked and we saw that no one is going to want to switch with Charlotte and Collins because nobody wants Collins. So there's no danger of that. So now I have to go through the Elizabeth, Darcy, maybe Jane and Bingley want to switch with them. Well, if I look at Elizabeth ended up with Darcy, that's for number 2. Jane ended up with Bingley, that's for number 1. Is there any danger of anyone wanting to switch with Jane? With someone wanting to switch with Jane? Yes. But is there any danger of Jane being amenable to a switch? No. Because Jane has her number 1 choice, Jane has Bingley, Jane is happy. Jane is not going to be open to a switch. So I don't have to check any pair that involves Jane. So do you see how there are 6 pairs to look at? By noting that Collins is a loser, that makes it easy. By noting that Jane has her favorite, that makes it easy. I'm now down to just the Elizabeth, Darcy, and the Lydia, Wickham. All right, well, Wickham's number 1 choice is Lydia. So I know Wickham is not going to want to switch. Right? And so it turns out it's actually not too bad to show that this is stable just by a brute force. There are 6 cases to look at, but by a little bit of clever looking, we can quickly eliminate 3 by looking at Collins, and then by looking at either Jane or Wickham, we can eliminate 2 more, and then you just use the other one to eliminate the last. If you don't see this, you just go through the 6 cases. Now, when you have more than 4 people, that's a lot of cases potentially to go through. So if we have n people who are being matched with n people, how many pairs are there? So if you have n men and n women, how many pairs? I'm sorry? There's n pairs. And so how many ways can I choose 2 pairs from the n? And choose 2, which is roughly 1/2 n squared. So there's more pairs. It's not a tremendous number, but there's more. Okay, so let's start going through the algorithm slowly and see why it works. So it's really nice when you have essentially Nobel Prize winning mathematics, and you can describe it. I mean, we listed the whole algorithm in less than a page. Yeah, absolutely amazing. Just really simple, clever observations, but it has tremendous impact. It's been used in a variety of problems. This has led to math really bettering society. There's no question about that. The question, of course, is when you have multiple stable matchings, how do you come up with which one is best? And you then have to define what we mean by best. This is where I talked about some of the other possibilities that you can impose. A lot of people like taking something in the middle, because if you do it from the men, you get one matching. If you do it from the women's point of view, you get another. So maybe somehow try to find a way to split the difference. So a lot of times there's advantages in who gets to do things. And so you want to try to find a way to be as fair as possible. All right, so step 1, let each boy propose to his favorite girl. Each girl who receives more than one, all but the favorite. And so, for instance, here's the women, say, and here are some men. and the men are proposing. And so in step one, maybe we have something like this. I'm trying to think of what might be the worst possibility. Maybe the first n-2 all propose to distinct women, and then the last two propose to the same person. And so there's one woman who has no proposals, one woman who has two, and she chooses her best, chooses her favorite. Maybe chooses this one, and then over here, this one is rejected. We'll have to propose again. Okay, so that's step one. And then you just look at all of the rejected guys, and then all the rejected guys propose to their highest rated choice that they haven't proposed to yet. It doesn't say to do that here. That's going to be what's next. But I want to make sure that everybody understands step one. All the men just make proposals. If everybody proposes to someone else, we're done. But if multiple people propose to it, the same person, then there will be at least one man rejected. And then you look at all the set of men who have been rejected, and that's going to be the next step. So the boys who are rejected now propose to their second choices. Each girl receiving proposals chooses her favorite from the group consisting of the new proposals and the boy on her string, if any. She rejects all the rest and again keeps her favorite in suspense. This basically seems like step one again. The only difference between this and step one is in step one, each woman had 0 suitors initially. After step one, some of the women will have suitors. It's possible everybody might have proposed to the same woman. I gave the situation which had the fewest number of rejected men. The other extreme would be everybody proposes, then you would have the maximum number of rejected men. So maybe in our situation, we had a bunch of women like this, a bunch of men like this. And so he was rejected. And so he is 1, 2, 3, n-2, n-1, and n. So now what we have. So man n-1 is rejected. Say proposes to woman n-2. She chooses maybe man n-1 and rejects n-2. So now rejected. Again, I'm just doing a specific situation. You could have, of course, maybe 5 men were rejected on the first round, and then they're proposing to more people. Is everybody clear on how the second round goes? You're going to just have some number of rejected people, and they're going to propose. Is it possible that there's no one who's rejected? In this situation, instead of proposing to person n-2, whom else could person n-1 have proposed to? To n. And if they propose to n, then every woman would have a proposal. And every man would be matched with someone. So in a situation like that, when there's nobody who's rejected, then the process stops. As long as there's at least one person who's rejected, the process continues. Do you think it's possible for the process to continue forever, that we could get into some kind of cycle? That's the danger, is that we get stuck in a loop. Well, let's look at what it says. Each The boys who were rejected now propose to their second choices. Who are they not allowed to propose to? Anyone they've already proposed to. So, you have a man who's been rejected and he decides to try his luck again on the person who rejected him in the first round. No, you're not allowed to do that. Once they reject you, you are rejected. Why were they rejected? They weren't high enough on the list. The person who rejected them had a better offer, and they're never going to lose that better offer. So if you come back to them and said, have you realized you can't do better than me? They'll say, no, actually I can and am doing better than you. So you can never propose to someone you've already proposed to. So what's the maximum number of times a guy can propose? N. No one can propose more than n times. So each guy only has a finite number of proposals. And so eventually you can begin to see that this process will terminate. If there is ever a woman who's not holding any proposals, what must be true? I'm sorry? Someone else has two, but of course, if they have two, then they're going to reject one. So what do you know must be the case if after a stage, there's a woman who has no proposals? She might, but she might not. Eventually, we think she'll get one. But if you know there's a woman who doesn't have any proposals at the end of a stage, what must be true about the men? So we have n women and n men. If one of the women does not have a proposal, so she hasn't been on anyone's list yet. So what must be true about the men? If there's a woman who has no proposal at the end of a round, what must be true about the men? There's at least one rejected man. Because if every man had a match, there's n men. And the only way that every man can have a match is if every woman has somebody that they're holding on a string. So if there's a woman who doesn't have anybody on a string, if a woman doesn't have any maybes, then there has to be at least one rejected man. If there's at least one rejected man, that means we can do another round. So we know that we'll keep doing this as long as there is a rejected, as long as there is a woman without an offer. So continue while a woman has no offers means at least one free man. All right, is everybody happy on this? So we will just keep doing rounds until each woman has an offer. So the question is, will each woman eventually get an offer? Now that's the danger, is if nobody ever proposes to someone, we're in trouble. So why do we know that each woman will eventually get an offer? What must be true? We can go back and we can look at the image with 4 women and 4 men. How do we know each woman will eventually get an offer? Good. Each man has to rank everyone. You can't just say, as Darcy, it's Elizabeth or bust. You have to list everybody. And so we know that if you're a rejected man, you've ranked everybody. And so if your first woman you propose to says no, you go to your second, you go to your third, you go to your fourth. If you keep being rejected, eventually you propose to everyone. And if somebody has no proposals and you propose to them, you are considered better than nothing. So we know that eventually everyone has to. So maybe man 1 is rejected for quite a while, and then eventually someone accepts man 1 and man 3 is now rejected. And man 3 starts proposing to people, and then man 6 is rejected. And then man 6 starts proposing to people, and now man 1 is bumped out and is rejected again, and man 1 starts proposing to people. Well, there's only finitely many men, So eventually, everyone is going to be proposed to. Because as long as someone hasn't been proposed to, someone is rejected and they keep asking. Okay. So I drew a little, well, I didn't draw this. I stole this from the, why do you think I stole this? Does everybody recognize what that is on the right? So what is this? Sudoku. So why am I choosing a Sudoku board here? Well, I wanted to just list, say, the preferences of the men and the women 1 through 9. This has far more structure than a normal list of 1 through 9. You know, each column, so this is, you know, man 1, man 2, all the way up to man 9. And this is their first choice, second choice, all the way up to 9th choice. So this is, of course, a lot more structure than a random list, right? But it's good for descriptive purposes. Can anybody give me an upper bound for how many stages there has to be? So they said that eventually, and at most, n squared minus 2n plus 2 stages. And like any good mathematician, they don't give any justification or any inkling of where that number comes from. They just say, here is the answer. And of course, it should be obvious to you.
65.
Why 65?
81 minus 16.
So why 81 minus 16?
Is 81.
Okay, well that's using their formula. But I'm saying, if I give you an n by n grid, or more generally, so can you give me something that you can prove as an upper bound for the number of stages? So they say that it's n squared minus 2n plus 2. So yes, so if you put a 9, that's what you get. But I'm saying, we have to prove that, or we have to prove something similar. So I can prove something similar to this, not quite as good, but very easily. Can someone give me an upper bound for how many stages? I'm sorry?
N stages?
Well, if it's n stages, that's much less than the n squared minus 2n plus 2. So you're on the right track. I'm sorry, why n squared? So can someone explain why there's at most n squared stages? So what would be the worst case? What would be the worst case in terms of taking the most time to get through everything? Every man gets rejected n times. Okay, so why does that lead to n squared? So you want to have as many stages as possible. So how could you have as many stages as possible? How many people do you want to have in each stage? 1. So if you have 1 person in each stage, every time a man proposes, they knock off something on their list. There's n squared elements. So every stage, at least 1 more cell is crossed out. So it's going to take at most n squared stages before we're done. We can do a little bit better than that. On the first stage, how many things are knocked out in the first stage? N. So in the first stage, we know we knocked out n. So let's see if it allows me to draw this. Oh, good. Yes. So I learned I have to save the image in the background if I wanted to draw over it on the iPad. So in the first stage, so stage 1, we lose n cells. How many are left? Have n squared minus n left, right? Worst case scenario, 1 stage for each remaining. And then the total would be 1 plus n squared minus n, or n squared minus n plus 1. Right, because the first stage that was 1 stage, and we got rid of n cells. And then the worst case and everything else. Okay. So this quickly gives us that it's at most n squared. We get a little bit better. We get n squared minus n plus 1. The authors claim it's n squared minus 2n plus 1. Should I work to try to get a better bound? Okay, why? Well, so they say that it's n squared minus 2n plus 2 stages is an upper bound for how many stages. They're not saying that there's actually a configuration where that happens. But let's assume that there's actually a configuration where that happens. We're able to get n squared minus n plus 1. How good is that relative to n squared minus 2n plus 1? Am I off by a lot, by a little? It's pretty good. I mean, this is why we started the day with these plots. Right? When we looked at the ratio, oops, this should be over n squared, not over n. When we looked at the ratio, n squared minus 2n plus 2 versus n squared, very quickly, it's close to, roughly the same size. If I looked at the difference between n squared minus 2n plus 2 and n squared minus n plus 1, there's really not that much of a difference. And so I'm pretty much capturing the true limiting behavior very easily. And so if I can get close to the right answer with a very simple argument, that's great. Now, in practice, you run the algorithm and it's never as bad as n squared minus n plus 1. So this is a big difference between the bounds that you theoretically prove and the bounds that are actually realized. So just because they say it takes at most n squared minus 2n plus 2 stages doesn't mean that it actually takes that many stages. So what I was trying to do in my daughter's gymnastics yesterday is trying to consider some kind of bad cases and whatnot. What if we had maybe something like this where you have one person who's rejected and then the rejection keeps propagating all the way down here and then somebody pops out and you keep going like that? How long can it take? So my question for you for extra credit is come up with a set of preferences so that it takes order n squared steps. So I don't care if it's n squared over 2, I don't care if it's n squared over 1,000. Show me that it can be as bad as an n squared algorithm. Maybe the algorithm runs a lot faster. When we did it with the characters from Pride and Prejudice, how many stages did it take? It took 4. Now, if you look at n squared minus 2n plus 1, what is n squared minus 2n? I'm sorry, n squared minus 2n plus 2. If n equals 4, that's going to give us 16 minus 8 is 8, so that gives us 10. So this is, did I do it right?
Yeah, you did.
Okay. You never trust a mathematician to do algebra on the blackboard. That's why I use the iPad. Okay, so 4 is much less than 10. But again, these are really small numbers, so it could be misleading. But 4 actually happens to be n. So maybe it's an order n algorithm, not an order n squared algorithm. The algorithm might run faster than we expect. But when we're doing the analysis, we get this bound of n squared minus 2n plus 2. But in actuality, maybe you never have to do more than n steps. Again, I doubt it. And I think this example was contrived to be somewhat nice. But you can go through and you can look at all possible pairs for 4 people. So how many ways would you have to assign for 4 people? How many cases are there? So how many ways can we assign the preferences to the 8 people? So for each person, how many ways are there to order their preferences? 4 factorial. So how many ways are there to assign preferences to all these people? 4 factorial to the 8. 4 factorial is 24. So there are 24 to the 8 possibilities to look at. I can easily reduce it to 24 to the 7th. Without loss of generality, you might as well assume the first woman, Elizabeth, has her ordering as the same ordering as the men down below. Because you can just choose the men accordingly. So whatever her ordering is, that's going to be how we list the names. Once we've chosen her, then everybody else is. So we're now down from 24 to the 8th to 24 to the 7th. Oh, well, that's a factor of 24 savings. That's not bad. And from this point, unfortunately, that's about all we can do. And so you'd have to look at 24 to the 7th. 10 to the 7th, it's not too bad. 2 to the 7th, 2, 4, 8, 16, 32, 64, 128. So, maybe 10 to the 9th. So I think this is in the range that could be done by brute force with a computer. You could just go through and look at all possibilities. So if you want for extra credit, look at all possibilities of matchings of 4 people with 4 people and see what is the worst case. Is it close to 10? Is 10 actually realized? Instead of doing the case with 4 people, what could you do instead? What might be easier than doing 4 people? So with 4 people, we had 4 factorial to the 7 things to check. Instead of looking at 4 people matched with 4, what might be simpler? 2 people with 2 or 3 people with 3. So with 3 people matched with 3, there's 3 factorial to the 5th. That's not too bad. So 3 factorial to the 5th is not too bad to see that. Okay, so we've talked about how it's going to terminate in at most n squared minus n plus 1 stages. So we know that we're going to have a matching because everyone is going to eventually have to get a proposal. If there's not a proposal to some woman, then there has to be a rejected man who will keep proposing, and eventually he will hit that woman. And because there's only finitely many men and they all have rankings and everybody is ranked, everybody will eventually be proposed. So if there's ever anybody who has nobody, eventually one of the rejected men will hit them. So is everybody comfortable that the procedure will terminate? What's the only thing that we have left to prove? That it's stable. And so stability is actually not too bad. So we assert that this set of marriages is stable. Namely, suppose John and Mary are not married to each other. We have John down here, and we have Mary up here. Who should John be married to? We'll match maybe John with Jane right now, and we'll match Mary with Mike. Trying to come up with notation that's natural so we can think who they're matched with. So let's say that these two want to be matched to each other. So John would love to ditch Jane and go to Mary. So John prefers Mary to his own wife. So I guess actually I should do so. John wants Mary over Jane. Okay. So if that's the case, if John prefers Mary to Jane, the only way John could have proposed to Jane is if all the people he likes more than Jane have rejected him. Right? John cannot propose to Mary until all his higher choices reject him. So what do you know about Mary? She prefers her husband to John. She rejected John at some point. Mary rejected John and is happy with who she has. So there's no way John might be willing to switch, but Mary is not going to accept John. So we have a very simple proof that it's stable. So, in a lot of your math classes, you see fundamental theorems, fundamental theorem of calculus, fundamental theorem of algebra, fundamental theorem of arithmetic. This is a Nobel Prize winning theorem. And we basically did it in an hour. And could you do this in high school? Yeah. Could you do this in junior high school? I think so. I mean, we're just using some basic algebra. We're not using fixed point theorems. We're not using continuity and differentiability. We are just using elementary observations. Just because observations are elementary does not mean that it's not as good math as other stuff. This is phenomenal. Okay, so for the next class, what I decided to do is to just really drive home this notion of size. So how many of you have seen the gamma function before? Okay, so this is the generalization of the factorial function. It turns out if n is let's say, let's do n is a non-negative integer. It turns out gamma of n plus 1 is n factorial. So this function generalizes the factorial function. A really nice exercise, if you haven't seen this, is to prove this by integration by parts. So it's a nice exercise, if s happens to, what's the easiest value of s to choose? Nope. Why 1?
Or x, it's x to 0.
Right. So if you take s equals 1, then you're just integrating e to the negative x. Okay, that's not a bad integral. So you can evaluate this pretty easily when you take s equals 1. And then if you take s equals 2, 3, 4, you can do these, by brute force. And then in general, you can just do it by integration by parts. So it's a really nice exercise. Prove that gamma of n plus 1 is n factorial. How many of you have seen Stirling's formula? All right, so Stirling's formula says that n factorial is about n to the n, e to the minus n squared root of 2 pi n. And in fact, you can even be a little bit more precise, and you can even say what the error terms are. And you can have some nice convergence series expansion. And so I'll talk a little bit about how to prove stuff like this in the next class, because in a lot of what we're doing, it's important to get a sense of the size of functions and the complexity. Is this something that you should be trying to do, or is it just so bad that you basically say, we give up and we need another method? We cannot check n factorial objects when n is reasonable. If you have a somewhat old calculator and you try to plug in 60 factorial, I think you're okay. By the time you get to 80 factorial, I think the calculator says no thank you, and just gives you an error. It's an overflow error. And so when you have tremendous numbers like this, it's important to get a sense of how do you understand them? Can you get some rough estimates? And then of course, the other thing is just always using logarithms. When you have big things convert to a log scale, much easier to understand what's going on. All right, so this is a good place to stop.